Hello, everyone. Welcome to Geology 106. The time is 2:54, and we will be starting at 3 o'clock as usual. Today we're going to be talking about volcanoes, part 2, and we're going to be focusing on volcanic hazards, volcanic features. We're also going to, talk a little bit about, we're going to talk about plate tectonics and volcanisms, just briefly, just reminding you guys what we had already talked about during the plate tectonics module. And then we're also going to just barely touch on kind of and get you started on partial melting and how partial melting is generated in the crust and mantle. So, how's everyone doing today? Let's see if I can make this a bit smaller. See, I'll also post a link to these slides again in the comments here. I see that a few of you guys are here. How are you guys doing? Genesis is doing good. Good to hear it. Echo, nice to see you. Glad to hear you're doing good. Doing all right. I'm hanging in there, right? Talking about volcanoes now, though, so everything's good. Freaking love talking about volcanoes. Volcanic activity. We had a definitely demo-heavy lecture on Monday. Today will not be demo-heavy. I mean, demos are like the fun part. So, but today we're going to talk about a lot about the stuff that makes things relevant. So, should still be fairly interesting, even though I don't have lots of fun demonstrations to show you guys. Yeah. It's so funny. I see the number of people who are watching. It just tells me, there's 4 people watching or however many people. And it's kind of funny because sometimes the number goes up and then it instantly goes back down. And it's like, someone thought about coming and they're like, nah, not for me today. Almost about time to start here. How are the rest of you guys doing? Looks like we've gotten a few more people. Yeah, sometimes the viewer thing's a little finicky. Pretty good. Glad to hear that you're doing well, Alicia. let's see, did anyone have any questions, by the way, from either the lab or from any readings in the book that you kind of wanted to, if anyone has a question you want to just throw out there while we wait for a few more people to join the conversation? Go ahead and toss out any questions there in the chat that you might have, or stuff from that we talked about on Monday. It's definitely pretty common too to like first hear stuff and be like, yeah, that all makes sense. You know, that I'm with you, that I got it. And then you like go back to go like work on homework or stuff like that. And then as you come across things, you're like, maybe I don't. That's actually pretty normal. So don't feel bad if that happens to you guys. I would be surprised if it didn't, honestly. That is the nature of like math and science. So we'll also be having a Q&A afterwards today too. Let's see, I'll get to that question in just a sec. So we're going to have a Q&A afterwards too, but I am going to try and see if I can perhaps take off by 4:30 after Q&A. So I'm hoping lecture today will only be about an hour, and then to do some Q&A, live Q&A afterwards via Google Hangouts. Yeah, just seeing if I can make that happen. But if not, you guys are definitely my first priority here. So let's see, to prevent an eruption, could a government theoretically divert magma from central chambers? I think that magma diversion would probably in some instances help. Would it help though? Because in regards to like decompression melting, I'm kind of now starting to like think back to, because we talked a little bit about how like dikes and sills taking magma like away from stuff. Does that help to maybe lessen the chance of an eruption and whatnot? But one of the ways that turn to it in my book here too. One of the ways though that magma is generated is through like decompression melting. And we'll talk a little bit more about this later in the lecture, but essentially it's kind of like when you release, I still have this Coke here because I don't drink soda. I literally just bought this for the demo. So when you like release the cap on this guy and you release that pressure, right? Oh, hey, look, we still have some bubbles generating, guys. Still managed to generate some degassing. That release of pressure actually does cause some partial melting to take place. So I think I may have also misspoken too earlier. So we'll get into that though. Hopefully there's time. And in terms of like theoretically diverting magma from a central magma chamber, I think that that would be extraordinarily expensive in order just to be able to like get down deep enough where that's taking place. I'm not sure how near the surface that stuff actually is. And there's also a variety of kinds of eruptions too. There's, for example, Mount St. Helens was a really interesting eruption where the side of the volcano blew off because there was magma, I believe there was magma recharge and stuff was boiling down below. And when there's magma recharge, when magma is somewhat on the move, if you will, beneath the volcano, because there's a rumbly in its tummy or whatever, I don't know. There's a lot of earthquakes that get caused by that magma moving inside the volcano. And if there's magma recharge or if there's any degassing, like the volcano can actually like swell up kind of like a balloon. And one of the sides of Mount St. Helens in 1980 was actually doing that. It was starting to swell out, and there were lots of earthquakes that were going on because magma, etc., was moving inside the volcano. And one of those movements caused an earthquake the morning of May 18th, 1980. And that earthquake was powerful enough to destabilize the swelling slope. The slope basically was just too steep, and that shock caused it to destabilize and slide off of the, just the side of, we've got the volcano here, this bump that was bulging out. A volcano came, shook it, and then it just like fell off. And then that release of pressure caused the explosion out the side of the volcano. And Mount St. Helens isn't the only volcano to erupt with like a lateral blast. After St. Helens erupted, that really opened the gateway for a lot of volcanologists around the world who'd been looking at similar landforms around other volcanoes that were quite puzzling, because we'd not seen a lateral blast up until that point. We just not seen it before. So we didn't even really know that we didn't even really think of this as being a way that volcanoes might erupt. And so it produces these very odd landscapes, which is why I wanted to take you guys there. And volcanologists were then able to see like, oh, that's what causes that weird thing. And now I know why this other volcano in this other part of the world has that feature. So I don't really know if I'm basically, that's a long way to give you an unsatisfying answer, Alicia, that I'm not sure. But yeah, it's definitely an interesting question. How can we, looking at hazard mitigation for volcanoes, which is really important. Currently, where we're at is just in the stage of monitoring. And then if we see signs of an imminent eruption, rather than preventing the eruption from happening, we are more in like, okay, so let's evacuate and get as many people out of harm's way as possible, rather than preventing the natural disaster from occurring altogether. So that's where we're currently at with magma, or with volcanic eruptions in terms of hazard mitigation. I think that with a lot of natural disasters, that's it's difficult to prevent the natural disaster from happening, but it's important to study these things so that way we can see the warning signs and know when something is about to go bad, and getting as many people out of harm's way as possible. So that's an excellent segue too into the first part of our lecture, which is going to be about hazards. And it's a fascinating, I love talking about like hazard mitigation. And that's why next week is another week that I enjoy talking about. We're going to be chatting about mass wasting, as well as like floods and things like that, and rivers. So, but let's go ahead and hop on over to the lecture slides if you guys haven't already. We're going to pick up on slide 21. I found some memes for you guys. Who doesn't like a good meme? You have a black soul, black heart if memes don't bring laughter to your face. But anyways, looking at these memes really briefly, wanted to comment at least on the top left one, where it can't just be one person. A bunch of people are clearly trying to roast hot dogs over a active Pahoehoe flow. It's an active one because you can see that there's actually like lava underneath the crusted over solidified top of this Pahoehoe flow. And yes, it is insanely hot when you walk up to those things. I regret not going on a particular trip that would have costed me money, and I felt like a poor college student and didn't want to ask my parents for more money to go on this volcanology trip, but I totally should have, because some of my friends who went on this trip in college went up to one of these Pahoehoe flows just like that, and they, they said that it was extraordinarily hot. They actually got to dip their rock hammers into the active Pahoehoe flow, into the lava. And the pictures of like my friends who were doing that, they're all kind of like shielding their face from the heat because it's so hot. But I saw that picture of people trying to roast an obscene amount of hot dogs over the lava flow. And I was just like, geologists would though. Like, I see that and I'm just like, those are clearly geologists. Like, it's not some person who probably is just not, who's just Joe Blow who lives in Hawaii or something like that. I will bet you so much money that that is geologists specifically. Such a geologist thing to do. I don't know why. It just seems like I can completely picture that. And anyways, moving right along, enjoy the other memes. So let's go ahead then and segue into more serious topics about volcanic hazards. Looking at that next slide there, slide 22, we can really kind of see some of the devastation that these volcanoes cause. And we're mostly going to be talking about composite volcanoes at this point in time because they are by far the most dangerous. They produce a lot of the pyroclastic materials. Of course, shield volcanoes and cinder volcanoes still, have hazards, particularly with the gases. In this corner, or in this picture, this slide, there's a picture in the bottom left with some fire, and there's along the ground, there's an active Pahoehoe flow coming through there. And that probably is like a shield volcano that's occurring on. Sometimes things can catch fire. So even if the lava flow does not touch the thing, it still might be hot enough near the lava flow that it catches surrounding things on fire anyways. And then the fires can spread further. So still very dangerous, these lava flows, but Pahoehoe flows and Aa flows can usually be outrun by a human. And so, but most of the stuff with composite volcanoes, you can't outrun that. You're just screwed. And that's why it's so vitally important, especially for us in this state who live around numerous composite volcanoes, to understand the warning signs that something is coming. The top photo there on the left-hand side of that slide is showing some ash that is just completely consumed the landscape. Looks like we're looking down on a house there that is buried in a lot of ash. So before we go any further, and we look at slide 23, which we're going to list out some volcanic hazards. I first want to do a small kind of experiment with you guys, experiment, if you will, for the few of you guys who are here. And I'm going to list off some cities and towns in the Seattle area. And if you have ever lived in one of these, or currently live in, or know someone who lives in one of these, or you've spent a significant amount of time in one of these places, I'm sure you've heard of several of the places that I'm going to be listing off. But if you've spent a significant amount of time there, or know someone who has, or lives there, or etc., go ahead and put your name, write in the comments, yeah, I've heard of one of these places, and you can just leave that in there as I'm going. So I'm going to list off a number of cities. Let's start with one that is kind of popular: Tacoma, Puyallup, Ording, let's see, Buckley. I had relatives that used to live in Buckley. They live in Arizona now. Let's go ahead and talk about Yelm or McKenna. Moving into kind of like another area, How many of you guys have heard of Castle Rock or Kelso? Both of those are kind of south in our state. They're by Oregon. If you're driving down I-5 on your way to Portland, you'll pass through Castle Rock and you'll pass through Kelso. So Alicia's heard of them, which is awesome. I hope you guys have heard of Tacoma and Puyallup, and that's where the fair is, right? Relatives in Tacoma, family in Kelso. I know a lot of people in Tacoma. I have several groups of friends who live down there. So let's move more northward. I'm going to again list off some more cities. Stanwood. I also have family up in Stanwood. Arlington. How about Darrington or LaConner, Burlington. Let's see. I was looking at this map and I'm like, I don't know if I can actually read some of the names for up there that I would on this one portion of the map that I'm trying to read. It's not a very good map. I'm sorry, guys. It wasn't very high quality. But anyways, that's enough. You guys will get access to these maps in just a second. So the places, let's see, have friends in Arlington. The state fair is my life. I've only been to the Puyallup State Fair like once. I lived in Snohomish, so my family just went to the one in Monroe growing up. I didn't know what I was missing. But yeah, so I had friends like in Tacoma and family up in Stanwood and some of these places. Well, all the places that I listed, though, we're going to see in a few slides from now are places that are in hazard areas for volcanoes in our state. So Kelso and what was the other one I mentioned? Kelso and Castle Rock. Those are in the hazard map. They're in harm's way is what I mean. They're in harm's way in the hazard map that the United States Geological Society has put together for Mount St. Helens, and like Tacoma, Puyallup, and cities around that area that I listed are in harm's way of, Mount Rainier. And then the more northern cities that I mentioned, Stanwood, Arlington, Darrington, and north of that are in harm's way of primarily like Glacier Peak. And then the map's too blurry and I can't read the cities that are around Mount Baker, but we'll look at those slides in just a moment. You'll get to see those hazard maps. Those are just a couple slides away. But so it really is important that we study these things. It's important that geologists have gone out there and looked at the dirt in the ground in these cities and are like, oh, hey, look, there's a ton of volcanic ash here, or there's lahar deposits. And those are really dangerous, you know? It's really important that we know about these things. We know what a lahar is because, I mean, places like in Buckley, I guess my relatives, when they were growing up there, they actually had to do like drills in school around like what happened if Mount Rainier went off, you know, like kind of like earthquake drills almost. So important stuff to think about because this is very real and we live around it, and the school system isn't really talking about it. So we're going to talk about it today, guys. Additional volcanic hazards. I don't know why I used the word additional on that slide for volcanic hazards. These are kind of most of them. I guess we kind of talked about lava flows, and that must have been my thinking there for saying additional. But we're going to first be talking about, let's go down the list, pyroclastic flows. We're going to talk about lahars. And if you're not sure how to spell these words, don't worry. They're the headers for the subsequent slides. Lahars, ash. Ash is actually very dangerous. It's not just a nuisance. And we'll talk about why. Gases, sulfuric gases, etc., from the volcanoes. And believe it or not, we're not actually going to talk about it, but we're going to mention the fact that volcanic eruptions can cause tsunamis. It's pretty rare, my understanding. But I don't think the book really either talks about it either, other than just mentioning that it is possible. So let's go ahead and move on to slide 24 there and talk about pyroclastic flows. What is a pyroclastic flow? Well, depicted there, you can see on the bottom left-hand side of that slide, running down the side of this mountain is this really thick, dense cloud, right? And we saw from previous eruptions that there's like this ash column that goes up in the air, right? But sometimes there is this particularly dense cloud that runs down the side of the volcano. So they run down the side of the volcano, pyroclastic flows. They are driven by gravity because they're really dense. They're very heavy. They're very laden with ash and other things like pumice and whatnot. And that's what you're looking at in the bottom right corner of that slide. There's this dude who's walking up to all of these kind of white colored rocks. He's walking up to a bunch of pumice. Pumice isn't always orange. Sometimes it's kind of a lighter color, like what he's walking up to. And that was kind of the edge of the pyroclastic flow right there, after all the ash dissipated away. And that's like the edge of where all these giant pumice clasts came to in the pyroclastic flow. These things move fast. They're gravity driven, and they move up to 100 kilometers per hour. How fast is that? We live in the United States, Caitlin. We're not familiar with kilometers per hour. Well, it's 62 miles per hour. So freeway speeds. You can't outrun that. You're screwed, right? Hopefully it's not searing hot by the time it gets to you if you get caught in one of these. As I've mentioned before, kind of the third bullet point that we're going to talk about on this slide in regards to pyroclastic flows is that, again, they're that low density cloud of hot gases and fine ash, as well as sometimes other materials like pumice and whatnot. And and usually that cloud of hot gas and fine ash is on top of a layer of vesicular pyroclastic material. So this stuff is kind of like lower in the flow, and it just runs down the side of the volcano. Let's see. I saw some stuff pop up. Like an avalanche, but incredibly hot and possibly toxic. We're going to talk a bit more about avalanches next week, oddly enough, instead of with the cryosphere week, because avalanches are a type of mass wasting event. It's just that the material is snow instead of dirt. It is like, there are two types of avalanches. There's wet avalanches that are primarily like wet snow. And then there's like really powdery avalanches. This is like the powdery avalanches. That's just like a cloud of snow that's very dry. But it is not like the wet avalanches. The next hazard that we're going to be chatting about, lahars, are more like wet avalanches. So we have to be really careful with that distinction when we say like avalanches. It's like one of the avalanches, not both. So yeah, incredibly hot, and it is toxic. Pyroclastic flows have claimed many lives throughout history. It's what killed all of the people when Vesuvius erupted and buried people in Pompeii, if I'm getting those two names right. Maybe you guys saw there was an exhibit at the Seattle, the Pacific Science Center a few years ago, where they actually brought some of the artifacts that they found that were buried by, I'm pretty sure it was Vesuvius was the name of the volcano. Someone correct me if I'm wrong in the chat. I believe it buried Pompeii. And this whole city was completely buried and just smothered in an instant, and everyone died, you know, while they were sleeping or doing whatever. Most of them, I believe, were sleeping. I think it was a nighttime eruption. So these things, if you are also like really close to the volcano, these can actually incinerate you as well. Mount St. Helens was such a massive eruption, bigger than I think the ones that we're looking at in these photographs. And there were people who were just incinerated, I believe. Some people lived really close to like Spirit Lake, and what was his name? His name was actually Harry Truman. And I believe that he was incinerated probably because he was so close to the volcanic vent when the volcano went off. Not Harry Truman, like president or whatever. He just happened to also be named Harry Truman. So let's go ahead and move on then to slide 25. And then after we finished the kind of bullet points on slide 25, I'm going to actually show you on my phone again, just kind of a quick video of one of these things in motion. So on slide 25, a couple more photos there of some pyroclastic flows. What causes the pyroclastic flow? We talked about the eruption column, right, where you got this stuff that goes up in the air, this hot ash, right? Well, why is it that sometimes stuff runs down the side of the volcano instead of going up into the air? They're tied together. So pyroclastic flows are caused by a collapse of that eruption column. So the volcano violently shoots out all of this ash and material and gases into the air. And rather than continuing to rise and spread out, it's so dense that it falls back down on itself and runs down the sides of the volcano. So caused by a collapse of an eruption column. These sear and obliterate, as I said, everything in their path. So let's go ahead then and actually check out. I have something on my screen, my phone. Sorry, guys. Let's go ahead then and actually check out some of these eruption columns collapsing, creating a pyroclastic flow. All right, so I'll post these links too on Canvas. I have them here on my phone, not on my computer, so I can't like post them right this second, and they're not in the slide because this was kind of like a last minute thing that I decided to do. But we're gonna watch it here together. Let's make sure that my volume's good. Hopefully it doesn't come out glaring on the other side, the volume. I apologize. All right. So we're looking at the pyroclastic flow come down the side of this volcano. Oops, sorry. It's gonna race down here. And by this light colored deposit, I can tell that this is not the first time that a pyroclastic flow has come through here. Sorry, my hands are a bit shaky. So this is what it looks like in motion. Doesn't look like it's moving that fast, but again, these do move at freeway speeds. That's enough of that. There's more to the video, but I will let you guys watch that on your own time. Finish it off if you want to. So, there was another city that was also destroyed by a Vesuvius eruption. I don't know if I can pronounce that. It looks like the first part of Herculaneum. I don't know. Sorry, guys, not the best. But yeah, it doesn't surprise me that Pompeii wasn't the only one to get destroyed. because people just have a habit of being like, oh, look, it's so pretty here by this, really tall, like, mountainous feature. Let's live here. History, we just do this. We just keep doing it. So let's go ahead then and move on to slide 26 and talk about lahars. So this is more like that wet avalanche type of hazard, right? So lahar, what the heck is a lahar? It sounds so weird, such an odd word, and it's spelt so funny. It's water saturated volcanic debris. So if you have, do I have my ash here? Yeah. So this is some of my Mount St. Helens ash. I think I have more in a jar. It was given to me. Credits in a box behind me. Why didn't I think to dig that out before lecture? But anyways, so it's a bunch of ash, right, that is saturated with water. And you're like, water? Kaylin, I thought we were talking about like volcanoes, ash, lava. What do you mean water? Well, on a lot of volcanoes, such as like Mount Rainier and Baker, etc., there's usually a lot of snow and potentially glaciers from years gone by and accumulation and not enough melt in the summer. And, Baker's covered in snow right now. And so is Mount Rainier. Well, if those erupt, just as like when Mount St. Helens erupted, all of that ice and snow on the mountain, on the volcano, is going to melt. And it's not going to directly like just vaporize. It's going to melt and it's going to mix with any ash that is already on the volcano itself from previous eruptions, or from mixed with new ash, potentially like from pyroclastic flows and such. And it's going to form this really muddy slurry. And that is going to race down the slide of the volcano as well. And these travel great distances. Almost all the cities and towns that I listed, they're not in harm's way in terms of like a lava flow or a pyroclastic flow. They're all built on top of lahar deposits from these volcanoes that melted snow and glacial ice, etc., that mixed with volcanic tephra and ran down the side of the mountains, found its way into these river channels, and then overwhelmed the river channels and went for great distances. These things are quite terrifying. They're like walls of mud. So the 3 bullet points that I've got written down there on that slide is that it's water saturated volcanic debris, so it's like ash and pumice, but just completely saturated with water. And lahars are they're a fluid mud flow, thick like concrete. And they can occur on dormant or extinct volcanoes. I just threw you guys a curveball. What do you mean they can occur when a volcano is not active? And then you're just like, well, crap. What do you mean they can occur when the volcano is not active? It's more rare, but what can happen is if there is intense heavy rain on the flank of a volcano that has a lot of ash deposits on the flank of the volcano or other materials on the flanks of the volcano, that sudden like flash flood essentially on the volcano can water saturate this stuff. And then we have seen in past, heavy flash flood-like conditions on a volcano generate these mud flows by mixing with the stuff that's just happens to be lying around. And we have seen those cause devastation and move great distances as well. I don't think that we have seen that in our area in human history, but we have seen them in other parts of the world. So let's go ahead and fill in some bullet points on slide 27. The pictures that you're looking at, by the way, on slide 27, Both of those are from the Mount St. Helens eruption, I believe. The one on the bottom right there looks like it looks like a newer photograph than the 1980s. So that kind of has me questioning myself, but I'm fairly certain that that is from St. Helens. And I know the one on the left is from St. Helens. There's like a really large boulder in that photo on the left that this dude is standing next to. And that's like a really large chunk of the mountain that was brought down in the Lahar. And in the photo in the bottom right there, you can see, you're just like, what am I looking at here? Well, you're basically looking at a landscape that's just completely flooded with this ashy, cement-like, thick slurry. And there's actually like houses and debris that's been pushed around in that photograph. And looks like there might even be a school bus in there. And some like excavators or what have you. So filling in some of those bullet points with Lahars, this is kind of, again, summarizing what I said, but now you guys can put them in bullet points. Hot gases and volcanic ash melt that snow and ice that's on the volcano. And then after that happens, the melted snow and ice incorporates sediment, rocks, right? Not just the ash and other material, but any sediment that is there or further down from the volcano as this lahar continues to race further on, it continues picking up more sediment and more rocks as it encounters more of them, as it flows further and further away from the volcano, as well as like vegetation. It starts ripping up trees, and they'll even start picking up structures. So these things take out bridges, they take out homes and buildings, and they take them with them. You can actually go back and see footage from Mount St. Helens erupting and the lahar coming down the Toutle River. And there's literally a house, and the lahar has found its way into the Toutle River channel, carrying like a house with it. And the house, I think, just like runs into a bridge. And whatever is left of the house at that point just further gets demolished. We lost several bridges too in that eruption, in addition to homes. So last bullet point on there, sorry guys. Other triggers for lahars other than just a direct eruption, or that melting that takes place, the heavy rains. You can have near surface magma, like magma inside the volcano, come up in closer to the surface of the actual cone itself and melt snow and ice that's on the flank of the volcano, where, so if that magma gets really close to the surface, it could melt some snow and ice there. So triggers are going to be the eruption itself, near surface magma, as well as heavy rains. So let's go ahead then and check out some hazard maps. Slide 28 is a hazard map for Mount Rainier. What you're looking at there, Mount Rainier, is the kind of pinkish area that's near volcanic lava flows, right? So basically how these hazard maps are constructed is that geologists have been sent out by the USGS, and they have mapped where they've found deposits of lahars or lava flows. Ash just goes like everywhere, but mostly eastward of the volcano, because we tend to have a predominant east wind. But in any case, so what you're looking at is where they have found lava flows, which are those kind of pink color, and then the red, yellow, and orange colors are where they have found lahar deposits from Mount Rainier. And of course, red being a higher, either like a higher chance that you're going to encounter a lahar if you are there, or just like, there is more of this stuff in that location. And of course, it's going to thin out the farther you go, you know, and they've colored that from going from red to orange to yellow. Let's see. So the local area is basically set back decades. I'm not sure what you mean by the local area is set back decades. Go ahead and clarify that for me. There will be a bit of a delay before I see it though. Let's see, if this event happens. If this event happens at any one of our volcanoes here in our state or like in Oregon or wherever, it does really set back the area. The May 18th, 1980 eruption. By the way, how hilarious is it that your volcano lab is due on the 40th anniversary of the May 18th, 1980 eruption? I just saw that the other night and was like, oh, that's ironic. But anyways, that eruption devastated the economy for a little bit. Ominous, right? I think that the government, I was just watching something last night about it to refresh my memory. They sent a bunch of money to places like FEMA and the Small Business Bureau, etc., money to help rebuild. And the total amount of money that the government gave to all of these programs as a result of that eruption was the equivalent of like $3 billion some dollars in today's money. It was, you know, back then it was only like 1 billion, but today that's like 3 billion. The irony, right? Ominous indeed. So I was totally going to take you guys to Mount St. Helens this weekend too, because I bet that there will be a lot of people, would have been a lot of people up there, volcanologists and other people going back for the anniversary. Just as kind of like memory and stuff. Let's go ahead and look at the next hazard map on slide 29. This hazard map is for Mount St. Helens itself. This map has some kind of like tan color on it, and that is like regional lava flows basically. So in the past, there have been larger instead of more localized around the volcano itself. There's been more regional lava flows, but goodness knows how long ago that was. That was not in recent history. Not recently. So in that hazard map, you can see that like the North Fork of the Toutle River there is hit pretty hard with lahars. That's the giant red mark at the top of the map, right? And then you can also see though that all along I-5, there's lahar hazard there as well. They found lahar deposits there too. And pretty much all the rivers coming off of the mountain are going to have those lahar deposits in it. So let's go ahead and move right along to slide 30 and take a look at that hazard map. That is a combination hazard map of Glacier Peak and Mount Baker. And if you would like these hazard maps and would like them in higher quality, you can actually Google them, just USGS hazard map name of volcano, and you'll be able to go to the USGS website, and they have these maps out there for free because they want to inform the public. That's what they made these for. It was for you guys. So Glacier Peak, you can see at the bottom of this hazard map on slide 30, Everett is right at the very bottom. We're not in Everett. We are not in the path of, we haven't discovered any lahar flows, and we have no reason to believe that there would be a lahar all the way down there. But starting up around Arlington and Stanwood and Darrington, you can see lahar flows, deposits that have come off of Glacier Peak. So anywhere that there's yellow, red, and orange on that map is lahar danger zone. There have been lahars there in the past, and it's quite possible that they could be there again in the future if these volcanoes reactivate. So before I move on from lahars and start talking about ash as well as gases, I do want to like explain to you guys, my students, one of my goals is to inform you guys about how you can know yourselves. Like, well, does that mean I should, just stay as far away from these places as possible? Should I just never go to Stanwood or Arlington? Should I just never drive through these places? That's not what that means. Phew, sigh of relief, right? What it just means is that if you are in these areas, if you live in these areas, it's really important that you pay attention to if warning signs do develop on these volcanoes. We monitor our volcanoes pretty well in this country, especially Mount St. Helens, because it's super active by comparison. Should factor that into my down payment, right? And next week's going to help you guys out with that too. Factoring into your down payments and stuff. I literally call next week's lecture the Where Not to Build Your House lecture. And anyways, this factors into that too. What we need to understand about volcanoes, as well as knowing where we've found these deposits in the past, is understanding that when volcanoes do start giving off warning signs, and what are those warning signs? You guys are like, well, I don't know what the warning signs are. The warning signs are swarms of earthquakes. So when you have multiple swarms of earthquakes on a volcano, not just like one, but like a bunch of them, it's good to be alert at that point and watch for further signs. If the volcano starts leaking gases, right, that is certainly an indication that stuff's on the move in the volcano beneath the ground. And if cracks or fissures start opening up on the volcano, like literally just the ground is kind of like starting to go like this, right? And you start seeing these cracks. That's also probably a sign that there's some swelling of the volcano going on. And in some cases, you can literally just see the volcano swell. We have photographs from St. Helens showing the progression of the flank of the mountain just swelling up in the day, like the month prior. Just literally this giant bulge appeared on the side of the volcano. And people were like, that doesn't look right. Yeah, vacation time, exactly. And then there were many, and that's the thing, is that people don't hear these warning signs. Many swarms of volcano or of earthquakes on volcanoes, releasing of gases, cracks opening up and swelling occurring, and people are like, I was told to evacuate by like the local government, who are consulting like the volcano people, the volcanologists, but I'm gonna stay here because I like my house and I got, my stuff's in my house. Like, no, get out of there. That's the biggest problem, honestly, is with any natural hazard, is people not listening to the local government and the scientists that are monitoring things. If you're told to evacuate, evacuate. Don't wait, get your stuff and go. Grab your dog, grab your cat, and get out of there. Grab your family. Hopefully they got the message and are capable of understanding that, unlike your pets. Hopefully they don't need you to grab them to drag them out of there. But yeah, so evacuate if you're told to. That's really how you know. I honestly, I have family that lives in Stanwood. I'm not going to tell them that they need to move like pronto, but say Glacier Peak starts, showing some signs, and some volcanologists and the local government start getting worried, you bet I'm going to call them up and be like, so if you're told to evacuate, get the heck out of there. Just threaten to pull emergency services, right? Yeah, so, and also we really saw this in was it last year or the year prior? The volcanic island off of New Zealand. I was watching more on that last night as well. And there were signs that that volcano was going to go off. And this was literally like 1 or 2 years ago, volcanic island off of New Zealand. It did, some of you guys might remember, it did explode. And there were lots of tourists on that island, and just over 20 tourists died because the volcano erupted. And volcanoes tend to let you know when they're going to erupt. Like I said, all those symptoms that I just told you about, they usually do that before they erupt. And they usually give you like more than a few minutes notice. They give you like days, if not months, of notice that something's happened, could be happening, and that something could go very wrong. And I don't know why, but people didn't listen. So, and people died as a result. Anywho, hopefully that gives you guys some understanding of like, when do I need to be worried? When do I need to be alert? When do I need to be anxious? It's like, just know things in the back of your mind, these things in the back of your mind, and be alert when those symptoms start happening. And if the local government or scientists tell you to move, get out, you know. So let's go ahead then, and if you guys have any questions about that too, go ahead and leave them in the comments down below. I don't want to leave you guys like hanging, being like, no, I'm terrified, I live in Stanwood. You know, I don't want you guys to like leave this lecture like horrified, not knowing, not fully understanding like the what to do and whatnot. Don't leave this having nightmares. But anyways, let's talk about the next kind of hazard. Let's talk about volcanic ash briefly for a slide. What is volcanic ash? What is this stuff? You know, I know it's ash. I've been told so, right? For the longest time, I didn't know what ash was, right? I'm like, it's ash. Basically, ash is just tiny, tiny fragments of material. This was molten rock at one point, but when that violent eruption occurred, it just blew into the teeniest, tiniest fragments. And not only did it blow into the teeniest, tiniest of fragments that we call ash, it also solidified pretty much instantaneously. So this stuff thus is the equivalent of glass. It didn't have time to form these pretty minerals, microscopic minerals. It literally just froze instantly and became glass. So tiny fragments of glass, right? Tiny fragments of glass. What does that mean? That means you don't want to breathe it. So should you ever be caught in an eruption, make sure that you put on some kind of mask, eye coverings if possible. And that's what you're looking at photographs of in that corner, is you see people have kind of sunglasses on or glasses on. Not that that's super helpful, but good enough, right? And they're all wearing some type of facial covering because you don't want this stuff in your lungs. That glass is going to tear off your lungs. Thought ash was soft. It is soft in terms of like, if you touch it, it's going to feel like a really fine powder. But on a microscopic level, if you were to put this stuff under a microscope, you would see sharp edges on it. It's just that they're so tiny that our hands aren't really going to feel like such a tiny prick. It's so tiny. But your lungs will. Your lungs absolutely will. And so tiny fragments of ash that can cause respiratory problems. That's kind of the second bullet point on there, is that this is a hazard in terms of causing respiratory issues. It scratches up your lungs. And also it can ruin aviation and mechanical equipment and stuff. You can't fly planes through ash clouds because it will destroy the engine. These small, tiny shards of glass will just rip it all up into shreds. And so these cars in the background, honestly, I would not have started my car if I was in one of those pictures there. Both of those pictures are from Mount St. Helens, by the way. And the diagram there in the top corner shows the extent of the ash deposits from the May 18th, 1980 Mount St. Helens eruption. So what you're looking at there, the color coding, because there's yellow, orange, and red. Yellow means that there was just the tiniest bit of ash deposits found, up to 1/2 inch of ash deposit from that eruption. And then orange means that there was 1/2 inch to 2 inches thick of ash deposit. And then red is 2 to 5 inches of ash deposit that fell. The picture in the bottom, I don't think I said this already, but the picture in the bottom right is, I believe that was photographed in Ellensburg, which is like central, kind of the center of Washington State. And I don't know if you guys can tell, but in the background of that photo, the streetlights are on and it's the middle of daytime there. The ash was so thick that the streetlights turned on. It clouded out so much light that the streetlights came on. I think that the photo on the left of the man that looks like a fireman, he looks like he's got a fireman's hat on. I think that photo was taken in I want to say like Yakima or Spokane, maybe even, just all the way over there by Idaho. So let's go ahead and talk about slide 32 briefly, just add a couple bullet points to the gases hazard. So sulfur dioxide gases are primarily what are most toxic to us. And these sulfur dioxide gases are definitely deadly toxins to humans and animals. That's why you see in the bottom right there, a volcanologist sampling. They're trying to collect samples off of a volcano of the gases that are being emitted. And I bet that they're probably also going to try and scrape off some of the surface material where those gases are being expelled from. The bottom left photograph there is from 2018. Those are some Hawaiian residents, I believe, who are being evacuated because of the gases that were being emitted from the fissure eruptions in Hawaii that summer. That's pretty much all we're going to say about volcanic gases. Excuse me. Let's go ahead and then talk about some other volcanic landforms. So that does it though for hazards, what we're going to chat about in terms of hazards. Let's now, we talked about the anatomy of a volcano, right? Earlier we talked about how, let's see if I've got I didn't get my slides printed today. My diagrams printed today. Oh, you know what? I have one right here. There we go. Ta-da. So we talked about some of these things. We didn't really talk about laccoliths. Make sure you know what they are. It's pretty simple. We talked about sills. We talked about dikes, right? We talked about like ring dikes and sheet dikes. We talked about the volcanic conduit or volcanic pipe, as some may call it. Some call it the volcanic neck as well. That is, all three of those are acceptable terms. And the vent, which is where the top of the volcano is and stuff comes out of the top, tippy top. Well, let's talk about some more terms that go kind of beyond the basic anatomy of a volcano. So there's slide 33 there it gives a brief list of the forms that we are going to be, you know what, I'm going to leave that open. I might need that later. We're going to be talking about calderas. We're going to talk about fissures some more. We are going to talk about this amazing thing called flood basalts. And we're also going to talk about volcanic necks. The photos there, the one on the bottom left is fish. Oh no, it's called shiprock. Yep. It's shiprock in Oregon, I believe. Oh, now I'm second guessing myself. Now I have to Google it and make sure that I'm right. Yeah, it's called Shiprock, Oregon. It's literally like in the middle of nowhere. But it's pretty cool to go to. That was actually underwater when that volcano formed and erupted. Anyways, it's a caldera, and we'll be getting there. That's what you're looking at. It's the remnant of a caldera. And then on the right-hand side are some students from our school who went with me to tour Central Washington University's geology department. And Nick Zettner took out all the community colleges that came to go see some of the flood basalts that are in Eastern Washington. And so we're all posed doing some interpretive dance moves, I guess you would say, in front of these flood basalts. So let's move on then to slide 34 and chat about calderas. What the heck is a caldera, Caitlin? A caldera is a collapsed, like, volcano, it's basically like a collapsed volcano. I think that I can kind of draw this out for you guys. I think it's kind of better when demoed. You can see it there on the slide depicted, right? But still, for a lot of people just looking at that, it still kind of seems very abstract. So we'll walk through it. So calderas, once formed, are basically these steep-sided craters. Usually they're less than 1 kilometer in diameter. That's kind of the first bullet point on there, is that they're those steep-sided craters. The second bullet point on there that I have written down is that they're formed by the summit of a volcano collapsing. And that happens after all the magma in the chamber below has been drained out, after it's erupted, all of its material. So let's kind of sketch this out just a little bit. Make sure I don't hit my thing behind me. All right. So basically what's going to happen is you'll have a volcano here. Really need to kind of exaggerate this a little bit more for this demo, for this drawing. And then there is a conduit up through here. And going with our kind of cartoony depiction, there's a magma chamber below, right? Well, to start with, this thing is full, right? You know, it's full of material, and that helps like support this other stuff too. So if an eruption occurs, right, and then we empty out the chamber below and the conduit, now there's all of a sudden a vacant space, a very large vacant space. Maybe we didn't completely empty it out. Maybe there's still some in here going down. I don't know. But a ton of it has left the building. And it's like, you know, you've basically just created this cavity beneath. Oh, this marker is reaching the end of her life. But there's this cavity beneath all of this material here. And so all of this material collapses and falls in. And as a result, what it ends up kind of looking like is this crater, because all of these blocks of material they'll kind of fall downward as like blocks of earth that fall down in and move downward into the crater. And that's what you're seeing depicted on that slide. Only they don't do as good of a job of showing the emptying of the magma chamber below. And they kind of leave it colored in red. But it really is formed by the collapse of the summit of the volcano back on itself after it's emptied out a significant amount of material and created a void in the ground below, right? It's like a collapsing mine tunnel. You know, you've removed a bunch of material from underground, then the ground on top of it can't support itself anymore, and it just collapses in. Does that make sense to you guys? Hopefully. Let me know if you're just like, Caitlin, I'm lost. And we'll chat about it. All right. Settling on some rocks. Slide 35 is just a couple of beautiful calderas that have formed. Yeah, like removing a house's foundation, but leaving on the roof. Exactly. It's also kind of, yeah, it's just like removing stuff from underneath and then all collapses down. So slide 35 is just some gorgeous photographs of calderas in other parts of the world. A very famous caldera in the Pacific Northwest is in Oregon. There's Crater Lake is what it's called, because these things form craters on the summits of these volcanoes where there would be the top of the cone of the volcano. It now just is a crater, right? So that's what you're looking at in those two photos, is you're seeing these kind of almost cone-like features, but there's just a gigantic crater in the top of it. Not like a vent, but a really big crater. And then there's like Wizard Lake in the middle of Wizard Island in the middle of Crater Lake. I haven't been there yet. I'd like to go. People go boating there. Is it safe to be on a caldera? Depends on whether or not that volcano is still active. Once the collapse has occurred, usually it's all settled out and it's pretty done, you know? If you look at the photo on slide 35, the bottom photo, there's actually like a city living in that caldera. I hope that's an extinct volcanic island. I hope so. Lake Toba in Indonesia. Yeah. So it's safe to be on a caldera, provided that it's not like an active volcano. Mount St. Helens has a caldera on it due to like some collapsing of the summit of the volcano. And then also it's missing the north side of the volcano because that got carried away in Lahars. Literally the north quarter, the north, like 1/4 of Mount St. Helens is missing. It's not missing, it's strewn about all over that hazard map. That's the reality of the situation. Yeah, it's safe to be on a caldera. People go boating on like Crater Lake, and people go like hiking on Wizard Island. I believe that volcano is very dormant. So fissures. Let's go ahead and switch gears and talk about fissures. Fissure eruptions, we already chatted about this. It is a fracture or crack in the ground that opens up and lava is emitted out from it. That's pretty much all that we're really going to say about fissures. And I have depicted here one of the fissures from Hawaii in 2018, spewing lava that was on the Big Island. There's also a diagram there on slide 36 showing the flow, just kind of the lava fountaining out and then spreading out from that fissure. Let's go ahead and look at slide 37. This graphic is in your book, this block diagram and photographs. I don't know, it's the same thing, but just slightly different. I don't know, I like pictures. So you can see another fissure there where this lava is just flowing out and away from the fissure. And what you're also seeing there on the right-hand side of that photo are these, that's a hardened lava flow. It's not an active flow. It's looks like it's been there a while. It doesn't look like it's still kind of red or anything. And that's kind of showing that flow that at that time had kind of spread out from the fissure. Did you guys know, we mentioned it on Monday, but we actually used to have fissure eruptions here in our state. So moving on to slide 38, we're going to take a look at some of the fissure eruptions here in our state. And these fissure eruptions in our state that took place in history were actually pretty unique in that the amount of lava that came out of these fissures in eastern Washington was stupid. It was a ridiculous quantity of lava. The lava from these fissure eruptions covered not only parts of Washington, but also Idaho and Oregon. The map there on slide 38 in the top corner, there's a bunch of brown, and labeled on it is Columbia River Basalt Group. That's the extent. The brown is the extent of the lava flows. This did not all happen all in one go. It happened kind of as a series of eruptions over time, but it was all from eastern Washington mainly that those fissures opened up and this lava poured out from there and covered all that brown area. That's an insane amount of lava. And get this, in some areas of eastern Washington, those flood basalts are 3 miles thick. 3 miles. That's a big distance. That's really deep. So flood basalts, what bullet points can we add onto our slides about flood basalts? Let's see. We can say that they're, oops, I made a window disappear. These usually come from fissures. We can add that bullet point on there. And these also typically, when you have molten lava that flows great distances, they usually create these kind of basalt plateaus. And that's what you're looking at in the bottom picture there are these plateaus. That's a gorgeous photograph from eastern Washington, probably Frenchman coulee, but I'm not positive. We won't talk about coulees. I'm sorry, guys. But Nick Setner has a lot of information online, I think, in his lectures about several of the coulees out there in eastern Washington. Coulee basically means, in my opinion, it's kind of like a deceased waterfall. So what you're looking at there in the bottom picture used to be a waterfall at one point. And you can see multiple layers of basalt there, and those are actually separate lava flows. Like I said, this this did take place over time. It was a series of eruptions, not just one eruption that took place and covered that amount. But even still, it is still a mind-boggling amount of lava. Even for geologists, we sit there and we go, good grief. You know, you were having a bad day, right? So, oops, hold on a second. Oh, I lost my bullet points for this slide about flood basalts. But in any case, on the next slide there, on slide 39, you can see these basalt columns. Hold on a sec. I have to get a few things back in order. Okay, there we go. Sorry for the momentary distraction, y'all. At the bottom of that picture, does anyone recognize that scene? Anybody been there? I bet at least a few of you have. Well, there's only 7 people out of my class watching right now, so maybe not all of you guys have. Anyways, that's the gorge in Washington. There's a lot of concerts that take place out there. I shockingly have not been to one despite living in this state my whole life. Whatever. Anyways, that's the Gorge Amphitheater in Washington, Eastern Washington. Lots of concerts take place out there, and it's just gorgeous. And that is all flood basalts. And what you're looking at when you go to almost anywhere in Eastern Washington are flood basalts. It's the majority of stuff, geologic stuff out there to see. There is other stuff and other erosional features that have cut into these flood basalts that are just absolutely magnificent. But mostly in terms of rock, what you're looking at are flood basalts. Typically these form these like columns, right? And we call them we call those columnar basalts. We're going to talk about on the next slide how those columns form. But are you guys seeing there where it says Columbia River basalts? The flood basalts from Eastern Washington they're named after the Columbia River. We call them the Columbia River flood basalts, or CRBs, Columbia River basalts, CRBs. Someone out there is familiar with the gorge. Yeah, isn't it beautiful? And what you're looking at there is flood basalts, as well as, we will probably talk about this later because I can't help myself, erosional remnants from these ridiculously massive floods that took place at the end of the last ice age that went through there and ripped up the landscape and caused basically where we see like the Columbia River and the channeled scablands. You had these supermassive floods come through and destroy everything, creating these amazing river channels. Anyways, let's move on to slide 40 and talk about columnar jointing. When you go to Eastern Washington, when you go to the gorge or wherever, you're going to see this at some point in your drive. If you're looking, you will see these just columns of basalt. You'll also see them in a lot of gardens and landscaping. If anyone lives near the Alderwood Mall, like I do, out by the food court area, out by they have a restaurant out there like Claim Jumpers, and then a movie theater. They've actually used columnar basalt in their landscaping. So you can go there and see this kind of hexagonal column of brown rock and you go, I know what that is. Caitlin taught me about that. Anyways, columnar jointing is what that is called. And it occurs as a result of shrinking of the cooling basalt. So as the lava cools, particularly when you have these large ubiquitous flows, these very thick flows. So we're not talking about like the surface of a Pahoehoe flow. We're talking about a flood, a very, very tall, thick flow of the salt. As it slowly cools, because it's going to cool off, it's not going to cool off like slow enough that it's going to be able to form lots of gorgeous crystals like a gabbro, but it is going to cool off slow enough that as it cools, it's going to shrink and these fractures develop. And they develop in this 6-sided hexagonal pattern. And I believe that it's because that's just the most efficient way to cool a surface. This is very similar to how, like, I believe mud cracks form as well. As you know, mud cracks kind of dry out and they tend to do 6-sided patterns, not always. But yeah, the columnar jointing is a result of the material shrinking as it cools off. That's the basics of columnar jointing. All right, guys, we're so close to being done. Almost done today. Woohoo! So let's take a look at other volcanic landforms. Let's take a look at volcanic necks or volcanic plugs. What does this mean? This is when you have, shall I do another drawing? I'm feeling another drawing. They drew stuff and I really want to draw it myself. So we're going to. So this is when you have a volcano. Got my vent right here. Got my conduit here, or volcanic pipe. Right? Spewing stuff. All right. So long after eruption is done, much time passes. The material, why not? The material in the conduit and probably below as well solidifies and turns to stone. So there's material there. Rather than erupting out and emptying, it literally solidifies in place and just turns to stone there. A great amount of time passes, and let me fill in my kind of volcano because it'll help with the demonstration. Volcanoes, like these composite volcanoes, remember, they're made out of alternating layers of lava and ash and tephra, whereas this is just straight up solid rock the whole way through. What does that mean? That means that this purple stuff, the volcano, has some unconsolidated material, and it's not going to stand up as well to weathering because it's only alternating layers of like lava flows and then more like, you know, pyroclastic materials that are a lot easier to erode away. And that's precisely what happens over time. So as, you know, this volcano has gone extinct and whatnot, the elements continue to erode things away. And then you're left basically with this protruding, right, volcanic neck. And then you can like walk up to these things. Oh, there's flat land. But anyways, so you're left, hopefully that drawing kind of helped. I have too much stuff over there, too many rocks. Hopefully that drawing kind of helped. And that's what you're left with. And that's what you're looking at on slide 41 is you're seeing that is the conduit. And the material in the conduit of the volcano turned to stone. And then the volcano around the conduit eroded away. And the solid stone in the conduit is a lot tougher. It can take more of a beating from the elements, and it sticks around, and the rest of the stuff gets eroded and carried away by wind or water. But that remains standing, and we call that a volcanic neck or a plug. right? So the one that you're looking at there is Shiprock, New Mexico. So it's eroded volcanic cones, expose solidified magma inside the conduit. The inside becomes the outside, question mark. Kind of. It's more just like the outside disappeared and all we're left with is the inside, I guess. I don't know. Kind of. So let's take a look at the next photo though, because when I first saw this next photo, it blew my mind. Like literally, I was beside myself when I came across this photograph. Slide 42, what you are looking at are the erosional remnants of a formerly underground volcanic network. So basically we're looking at this plumbing system and we're removing all the dirt and we're turning all the red magma into stone and just eroding away all the dirt. You're going to be left with some really weird looking features. And that's what you're seeing in this photograph. I wish I had had the time to print this photograph out so I could point to all the things. But in the center of the photo, as well as kind of off to the right-hand side of the photo, what I believe I'm seeing there, it looks like we're seeing some volcanic necks. We are also seeing some sheet dikes coming off of these volcanic necks as well. And we're even seeing kind of in the middle, there's like the volcanic neck in the foreground, there's like a middle ground, and then there's the far ground. Looks like there's a volcanic like ring dike in there as well, which is just super cool. So what you're actually looking at there in that kind of mountainous landscape used to all be magma underground. And you're seeing the erosional remnant of all of that. So that's pretty cool. I thought that was really cool. I hope you guys think it's cool too. But it's okay if you don't. I get it. I know. It's not everyone's cup of tea. Let's briefly chat about just kind of refreshing and bringing some of what we talked about in plate tectonics back to memory. That there is volcanism is really associated with plate tectonics. You get volcanism at spreading centers, right, where you can have partial melting in the mantle come up, right, and at these mid-ocean ridges where stuff is thinning. You can have you can have oceanic crust subducting that causes melting to occur, partial melting. And I think that what occurs there, I believe that I misspoke earlier in the quarter. I'm kind of getting ahead of myself, but I want to do it now anyways. Is that with that subduction of an oceanic plate, that oceanic plate is going to drag. It's not that it's increasing the pressure or that it's decreasing the pressure necessarily, but that you're introducing water into the system. And we'll talk about why that's a big deal and why that causes partial melting a little bit. We won't get too much into the mechanics of it. So going to slide 44, that's just kind of a really beautiful block diagram illustration of what's happening at those spreading centers that are like mid-ocean ridges. This can also, of course, take place on land though as well, and it does. And we're seeing that partial melting generate. The yellow depicted there is the molten material, and the red and the brown is solid material. And then you're like, yeah, we know about spreading centers, but what about the Ring of Fire? So if you look at slide 45, they've nicely kind of shown the distribution of volcanoes around the globe. And you can see that the majority of them around the Ring of Fire, majority of them take place at like subduction zones. And what we're seeing at like the fissures are more like, well, I just kind of said it. What we're seeing at like those mid-ocean ridges are more like fissure kind of type of things as opposed to like a single volcano. Looking at slide 46, talking about the generation of magma from solid rock, right? What we are looking at here is the addition of water at the subduction zone. So when you add water into this system, it doesn't need to be as hot, it doesn't need to be as hot anymore for melting to take place. Basically, I really need to explain one more slide a bit further down before I really get into that. It won't make as much sense yet. So anyways, but you can still see like the melting taking place at like a convergent plate boundary there. And then of course we also have volcanism at inside of plates, and that usually occurs, looking at slide 47, when you have a hot mantle plume. So for some reason it's just ridiculously hot there, and you get molten material coming up right through the mantle. See, it looks like it's 4:30 now. We're going to go a little bit over, guys. We're going to go a bit over. It's okay, though. We only have a few more slides. We'll still have Q&A afterwards. So this hot mantle plume will rise. It will cause some flood basalts, right? Perhaps it might even, start building up like a shield volcano and turn into Hawaii. Who knows? So let's go ahead then and take a look at slide 48, right? So this is a very complicated diagram. And a few of you guys probably had heart palpitations just looking at it. And you're like, I took this class because I thought it would be the easy science class. It's okay. It gets hard sometimes. This is one of those times. We'll get through it. So what you're looking at here in this diagram on the second to last slide is the geothermal gradient diagram. One side, the left-hand side of it, is depth in kilometers. So starting at, the surface of the Earth is 0 depth in kilometers, going down to like 100 kilometers below the surface of the Earth, 200 kilometers below the surface, 300 kilometers, etc. And then what we're looking at on the right-hand side of that diagram is pressure. So the numbers are different because now on the left-hand side, they're illustrating depth. That's what those numbers are representing. And then on the right-hand side, the numbers there are illustrating, okay, well, how much pressure is the rock in the, in the crust and the mantle, etc. How much pressure is being experienced at that depth. So you can see that at 100 kilometers depth, if you go over to the right side of the diagram, that's pretty close to where it says 25 kilobars of pressure. So that means that at about 100 kilometers deep, you're experiencing about 25, don't worry about the unit. It's just a unit meaning how much pressure is being experienced there. What is the force of pressure there? It's about 25 kilobars of pressure. Hopefully you guys are with me so far. So you can then continue looking down on the sides and be like, okay, so if I'm 300 kilometers below the surface of the Earth, the pressure there is between, it doesn't really settle quite nicely on the other side, but it's between 75 kilobars and 100 kilobars. So we're probably sitting at around 90, maybe somewhere kilobars. Hopefully that's making sense to you guys. How accurate is this diagram? Fairly accurate. It's pretty accurate for sure. Yeah, I think this is about it's pretty detailed. I would use it and for my homework and in school, if I were in a geology program. Now, would I use it as a master's or PhD student is another question. Not sure. I think it's pretty detailed though. So, of course, in nature, there will be some variations, but this is definitely the general rule of thumb. And typically in nature, this general rule of thumb is followed. So now let's look at the top axis there. That top axis, because you're like, why is this diagram so wide? And what's all the stuff in between? The stuff in between, let's talk about that now. That is temperature. So this is where it starts getting more abstract. So try to stay with me as I attempt to explain it. In this space in between, what they're illustrating for you guys is that on the left side of the diagram, we're going to say that we're at like 0 degrees Celsius versus on the left side of, or on the right side of the diagram, you're at like 2,500 degrees Celsius. So that space in between those two axes, the pressure and the depth axes, it's not that what you're looking at is physical space. You're not looking at space between point A and point B. We're really looking at just showing how temperature relates to depth and it relates to pressure. So basically pick a spot anywhere on that diagram in that square that you want. Just set your finger anywhere. It doesn't matter where. I'm putting my hand on the screen. Just put your finger anywhere on the diagram, right? Any point. Have you guys done this with me yet? Have you put your finger somewhere? Type yes. If you have, put your finger on the diagram. It literally doesn't matter where. Did you put your finger in the green area, the orange area, or the yellow area? There are 7 of you watching. I would like to see 7 comments. Did you put it in the green, the orange, or the yellow? Green for convenience. I like it. Oh, for a second, like the viewers went down and I was like, oh, someone left so they don't have to like put in the chat box. They don't have to participate. But then they came back. So all 7 of you guys are still here. Green. Awesome. Let's see, a few more of you guys need to put your finger on the screen and then tell me if you put your finger in the green area or in the orange area or in the yellow area. All right. Most of you guys are just being party poopers, I think, and don't want to like write where you put your finger. But in any case, I won't keep the few who have commented. Echo says green as well. The few of you guys waiting who have set your fingers somewhere on that diagram. So what I want you to do from wherever you decided to put your finger on the diagram is I want you to look to the left and see at about what depth you put your finger corresponding to. So my finger is on a line right now. They put a nice little graph grid on the diagram, which is really helpful. My finger happens to be resting on a line that correlates with depth in kilometers of about 250 deep. Yours is going to be different. That's okay. My finger is also in the green area too, by the way, but I'm going to move it to the orange area just to be different. So now what I want you to do is look to the right, I don't know my right from my left. Look to the right side of the diagram and see what pressure is correlating to where you put your finger. So mine was at about 250 kilometers deep below the surface, and the pressure there is 75 kilobars. So hopefully you found out what the pressure is at the spot where you put your finger. And now what I want you to do is look up at temperature. And my finger is on a line that correlates with 1,000 750 degrees Celsius. That's where mine is. So I placed my finger on a spot that represents Earth, a portion of Earth that is experiencing a depth of 250 kilometers deep. The pressure at that specific spot is about 75 kilobars, right? And here's the variant part. Some of, I had my finger on that same line and I was in green and I was like, I don't want to be in green. So I moved my finger over and raised the temperature up to 1,750 degrees Celsius. And what that means is that if a spot that is that deep and at that pressure happens to be 1,750 degrees Celsius, or and that puts it in the orange area. They colored it orange for us. That means that mantle rock at that temperature and that pressure and that depth is partially melted. For those of you who put your finger somewhere that was green, it means that at the depth, temperature, and pressure for your spot that you picked, it's not melted yet. It's not hot enough. It's not enough pressure or kilobars, whatever. And if you put your finger in the yellow area, then you're completely melted. You're not like somewhat mushy. You're completely liquid. So that's what that means is, and so basically you can have something that is, a depth of 100 kilometers corresponding to a pressure slightly above 25 kilobars. And if it's not very hot there, if it's like below 1,000 degrees, well, you can even go up a little bit higher, but it's still going to be solid rock. However, if you expose it to pressure or to temperatures that are higher than that, then all of a sudden you're going to start melting rock at that depth and pressure. So that is kind of what this diagram means. It will take a while for this to sink in. It always does. It's okay. But sit with it, mull it over. They've drawn a green line or a red line on there. What is that red line? Not the dashed red line. That's the boundary between the yellow and the orange, but there's a solid red line. And notice that that red line is entirely in the green. That red line is pretty much how temperature rises naturally in the earth with increasing depth. So you're wondering like, well, under normal average conditions, what is the crust doing? Well, so if you want to know at 100, at a depth of 100 kilometers, which is corresponding to a pressure slightly above 25 kilobars, what temperature is it normally? And the answer is where the red line is. So at 100 kilobars, go over until you hit the red line. And then once you hit the red line, look up. And whatever temperature that corresponds to, that's normally the temperature that the Earth would be. However, the Earth does experience changes in this depending upon if you subject it to a lot of pressure, or if you release a lot of pressure, or if you add water, or if you somehow introduce a lot more heat into at 100 kilometers depth. If you just suddenly are like, hey, look, I brought you a gift. It's a package of heat. You might end up, making the crust not be wherever that red line is. And you might push it over, to the side, and you might push it over enough to get it partially melted, or you might push it over enough to get it all the way melted. Who knows? And this is important to know because this is what controls the whole like partial melting. This is what occurs turning that mantle from something that is solid into something that is liquid and can erupt at the surface of the earth, right? Have I made that as clear as mud for you guys? Maybe. So let's talk about decompression melting really quick before we go. And we'll talk about, oops, I turned the pages in my book. And we'll also just chat a little bit about addition of water. Not much. You guys do have a focus question on this about the different types of partial melting. I don't ask you guys to explain the geothermal gradient, but it is really important for helping understand the ways that melting is generated. You first need to have an understanding of, okay, so what's normal conditions? Normal conditions at certain depths and pressures are found along the red line. Those are normal conditions. However, we can mess with the system and we can make it not be the red line and we can make it be somewhere else on that square that they've given us. All right, so decompression melting is one way that we can do that. Decompression melting. So let me go ahead and go to the next slide, the last slide there. Hooray, there was much rejoicing. Go ahead and go to that last slide there. The bullet point is kind of, the first bullet point has a word missing there. The mantle is what under normal conditions? Solid. The mantle is normally solid, not liquid. Mantle is normally solid under normal conditions. Again, that red line is completely in the green. It doesn't go into the partially melted or fully melted zones. So the mantle and the crust are solid under normal conditions. So then the next bullet point below there, let me go ahead and see, forgot what blanks I left for you guys. Pressure increases. So pressure increases melting temperature. What does that mean, Caitlin? Pressure increases melting temperature. If you guys go back to that, I have it right here. You guys go back to this diagram here. As pressure increases, we get deeper and deeper, and pressure is increasing and increasing and increasing. This line of what temperature it needs to be in order to melt the mantle moves. It's not in the same place. The temperature is not the same. All of a sudden, if I'm way deep down here, the temperature needs to be a lot hotter in order to melt the solid rock. So that is essentially what I'm trying to say there, is that as you go deeper and deeper, suddenly it's got to be a lot hotter in order for things to melt. And I think that might be one of the reasons why people seem to think that the mantle is liquid, because you're like, well, it's really hot down there. Wouldn't it be hot enough to like melt stuff? No, because of pressure. As pressure increases, it can't just be like a warm day. It's got to be like really, really hot in order to melt it. Hopefully that makes sense to you guys. So decompression melting then is triggered when you suddenly, at like a certain depth, if you were to somehow reduce the pressure at a certain depth, right? And then all of a sudden, it's not as, you're at a certain depth, but the pressure, you've changed things. So now it doesn't need to be, it's capable of melting at that temperature. Hopefully that makes sense. It's really hard to explain. So decompression melting is triggered when confining pressure decreases because you've artificially moved stuff around, right? So then that does it for all the bullet points that I put on the slide, but let's like chat. Just let me just comment before letting you guys go about the addition of water. So when you add water into the system, water also is like, oh, suddenly it doesn't need to be as warm for things to melt. So has anyone ever put salt on their driveway or sidewalk to melt the ice when it snows or when it's cold out? Or has anyone, hopefully you guys have probably heard or maybe seen that like in the Midwest, especially, we don't do it as much out here in our state, but like they'll salt the roads so that the roads don't ice over. Why? What exactly is going on there? Why does salt do that? Basically, there is something about the chemical reaction between salt and water that makes it so salt water doesn't freeze at the same temperature as just regular water. I still have my cinder in there. My husband came in here and was like, why are you bathing your stones? I was like, it was a demo, okay? It was an important demo. But basically, this water is going to freeze before like salt water will. If you add salt to water, all of a sudden it needs to be colder than, what is it in Fahrenheit? 32 degrees Fahrenheit, I think it is the freezing temperature of plain water. Whereas if you have a bunch of salt in that, it's lower than 32 degrees Fahrenheit. So water acts like that though with crustal and mantle rock. If you add water into the system, it's like adding salt. There's a chemical reaction that takes place with the rock material, with the water, that all of a sudden this mixture doesn't need to be as hot anymore in order to melt it, right? So you can all of a sudden, if you add water into the system and you didn't change the temperature, all of a sudden you could get a bunch of melting to occur. Because previously it was okay at that temperature, but then you added water and it was like, I'm not okay anymore. I'm having a meltdown, you know? So then, got to keep them clean, right? Got to keep my rocks clean. I can't tell you guys how many times I've cleaned rocks. Primarily when I come home from rock hounding and there's dirt all over them, or I dig them out of boxes that have been donated to the school and nobody ever looked at them and no one ever cleaned them because the rock hound who collected them never cleaned off his samples. I cleaned a lot of rocks last summer. I really shouldn't complain. It was fun. Wouldn't you like to be paid to clean rocks? That's great. The third way that melting is generated, that we start melting stuff down there, is if you just raise the temperature. I don't really know that we need to chat much more about that. I'll have you guys read about it, but it really is that simple. If you just suddenly raise the temperature to enough that it's like, oh, I am indeed at 300, kilometers deep, and I'm at this pressure. It was only at 500 degrees Celsius, but someone had to come along and just raise the temperature to 2000 degrees Celsius. All of a sudden things are going to melt because it's hotter, right? So that one's fairly straightforward. Yeah, thank goodness. Save the easy one for last. Yeah, okay, so with that, let's go ahead and conclude lecture for volcanoes. And if you would like to be included in the live lecture, go ahead and put your name in the chat message there. If not, I will see you guys then on Monday, and we will talk about mass wasting. And after next week talking about mass wasting, we will have our exam on the following Monday. So next week is going to be mass wasting, and probably I'm anticipating to also talk about rivers and floods and things. And then the following week, we'll have our exam, and we'll also start a new chapter as well. So I see that Noah wants to do live chat. I think a few of you guys, I know some people like emailed me and want to do live chat either today or tomorrow. I have a short-term memory issue. So even if you already like told me you wanted to meet today, please still throw your name in the chat as well. Help a sister out. I tell people that my spirit animal is Dory because my memory is not the best. My short-term memory specifically is not the best. Long-term memory is fine. All right. Mona would also like to get in on the live chat. Let me start getting that set up. So in order, Noah, I have your email address that you prefer to use. For the rest of you guys, unless you throw a different email up in the chat. Wait, is there a Google Classroom? No, there's not a Google Classroom. Bye to the rest of you guys. But what is going to happen is I'm going to look up your student email, and then I'm going to send an invite to you. So you will need to log into Google. It looks like you are logged into Google with your student account. So you went to Google and typed in your student email and then your password. It's the same credentials that you use to get into Canvas, except with like the .students@everettcc or .com or whatever it is. I forget because mine is different as an instructor. So hopefully you typed that in and then your password and whatnot, and go to your Gmail, your student Gmail account, and there will be an email there waiting for you that says like, hey, Caitlin Owens invited you to a meeting. Click this link and join the meeting. It takes me a few minutes though to get all the proper things and look up the email and whatnot. Oh, and now my internet's being slow. Don't do this to me. Let's be friends. All right, so I'm going to end the live stream now because I think I see that Noah and and Mamona want to get in on the live chat. I don't see anyone else. Okay, it looks like it's just going to be the couple of you guys. So I'll get those invites sent in just a moment, and I will see you guys soon. Bye.